I'm Roman. Welcome back to the series of videos Neural Networks from Scratch in Go, where we implementing neural networks from scratch in Go, but using this book Neural Networks from Scratch in Python as the main source of inspiration. Let's put it like this. And in the previous video, I continued to implement the activation softmax function. I had some, the previous video was shorter than usual, and I had some troubles understanding this particular line. I mean, this one with dot product, I thought that it won't work, but in between videos, I actually tried to run. Well, first I created this util function to print dimensions because it's, the function that returns dimensions for the math dense, it returns a tuple, and I cannot do something like this. I have to unpack it in this way, but I thought maybe I can do this. Yeah, same. So, and I tried to, let's run model. I tried to actually run the backward for the softmax activation function. So I have categorical loss backward method, then activation function, well, the softmax activation backward method, and it looks like it works. I mean, there is no errors, and I'm printing the util. No, it's not here. Ah, it's here. So I'm printing this one. Okay. So it looks like it works. I'm not sure if the logic is really correct. On the other hand, it looks like it is. So we'll see. We'll see once we will run the whole process and compare it with the one that we have in the Python. Also, while in between videos, I made a small refactoring. So right now the dag flat returns the math dense already, because previously I had it returning me two-dimensional slice. Like Go slice, and then I had to copy the whole data, which is not that good. So right now what we have, in order to calculate the Jacobian matrix, we created the matrix. So this is for this part. We're creating the diagonal. I cannot speak the diagonal without mentioning the diagonally from Harry Potter. I just cannot do it. Okay, I'm creating the diagonal matrix. Then I'm creating the dot product matrix between the single output and the single output transpose, which creates another square matrix. And then for Jacobian matrix, we actually just subtracting dot product result from the diagonal matrix. And that's it. And the last thing we need to do for the output is actually calculate the dot product between Jacobian matrix and the single t values, which is the row from the input. And that's it. So the next thing I'm going to do, and I'm still on the backpropagation chapter, is taking some time to actually properly dive into this, but some chapters I kind of skip pretty fast. Sometimes I need to stick with this. So there is one thing, it's command categorical crossentropy loss and the softmax activation derivative. I want to check there is some code, and I think in the end we'll code at this point. Yeah, so we kind of close it to the end of this chapter. We'll see if I will be managed to finish it in this video, or I will continue on the second one. Let's see. Okay. At the moment we have calculated the partial derivatives of categorical cross-entropy loss and the softmax activation function, and we finally used them. But there is still one more step that we can perform to speed up the calculation. Different books and tutorials usually mention the derivative of the loss function with respect to the softmax inputs, or even weights and biases of the output layer directly. I don't go into the details of the partial derivatives of this function separately. So it's kind of a combination. This is partially because the derivatives of both functions combine to solve a simple equation. The whole code implementation is simpler and faster to execute. When we look at our current code, we performed multiple operations to calculate the gradient, and even include a loop in backward step of the activation function. Yes, where is it? Activation function, probably this one. No, this one. I think they're about this loop. That's actually the first. I think that we didn't have the loop in the Pythons before. Well, I mean, during the implementation of this, it was all most of the time using the chain rule in some way. Let's apply the chain rule to calculate the partial derivative of categorical cross-entropy loss function with respect to the softmax function inputs. First, let's define the derivative by applying the chain rule. So this is the categorical cross-entropy loss, and this is this is the loss, this is the softmax. This is, I think, the input for the loss function. This is for the softmax. This partial derivative equals the partial derivative of the loss function with respect to its inputs, multiply it by partial derivative of activation function with respect to its inputs. So this is the loss function with respect to input. This is the softmax function with respect to its input. Now we need to systemize semantics. We know that the inputs to the loss function y hat are the outputs of the activation function s. Okay, I'm checking if I run simple model. Where is it? No, this one. We know that inputs to the loss function, inputs to the loss function is outputs of softmax activation function. Yes, this is the line. This means that we can update the equation form to, so we're replacing it. Now we can substitute this equation from the partial derivative of the categorical cross-entropy function, but since we're calculating the partial derivative with respect to softmax input, we'll use the one containing the sum operator over all outputs. It will soon become clear why. Okay. After substitution to the combined derivatives equation, we're changing this one. Now, as we calculated before, the partial derivative of the softmax activation before chronic and delta 2, let's actually do the substitution of the s, this one, with y hat here as well. We substitute it was like the, yeah. So we're applying this, the fact that in one case the input is the output of the second one, so we're substituting this one. The solution is different depending on if j equal k or j is not equal to k. To handle this situation, we have to split the current partial priority following these cases when they both match and when they don't match. Just like it had before for the loss function, right? For the backward, yeah. So, but for the loss function we had it, if they don't match we have the value of 0, if they match then we calculate the value. For the j doesn't equal k case, we just updated the sum operator to exclude k, and that's the only change. For the j equal k case, we don't need the sum operator as it will sum only one element of index k. For the same reason, we also replace j indexes with a k. Back to the main equation. Now we can substitute the partial derivatives of the activation function, both cases with the newly defined solution. We can cancel out the y hat from both sides of the subtraction in the equation. Both contain it as a part of the multiplication operation and in their denominators. Then on the right side, so we're discarding this, right? So where's connect? Wait. So we're discarding this, and then on the right side of the equation we can replace two minuses with the plus and remove the parentheses. So this one, this minus, and this minus. Oh. So instead we have this one multiplied by this plus sum. Oh, and yeah, and we can remove this one. Now, now let's multiply the minus y(ak) with the content of the parentheses on the left side of the equation. So this one, right? So we have this minus value, then we have multiplication between y and y hat, and then we still have a sum, which is now let's look at the sum operator. It adds y hat over all possible values of index j except when it equals k. Then on the left side of this part of the equation we have y hat, which contains y(ik), the exact element that is excluded from the sum. We can then join both equations. So basically this has became just a sum of the all combinations over j. Now the sum operator iterates over all possible values of j, and since we know that y from ij for each I is the one-hot encoded vector of the ground truth values, the sum of all of its element contains 1. Yes, because one-hot encoded vector has only one element equal to 1 and the rest is 0. So yes, kind of, it's something that case will be 0. Oh, it will be 1. In other words, following the earlier explanation in this chapter, the sum will multiply 0 by y hat, except for a single situation, the true label, where it will multiply 1 by its value. So we can simplify it further to, yeah. So we basically, this one, we're simplifying this one. And what it says that this y hat value will be 0 for most of the cases except one, where it's 1. So when the k equal to j. So it means that we can substitute, well, oh no, I confused. Y is the one hot encoded value. So when the j equal to k, this part will be 1. So we will have this value. And for the rest, this equation will be 0. So this is how we ended with this one. So this is the full solution. As we can see, when we apply the chain rule to both partial derivatives, the whole equation simplifies significantly to the subtraction of the predicted and ground truth values. It is also multiple times faster to compute. Well, that's true. I mean, instead of doing like lots of the loops and dot product operation, etc., if we can just do one subtraction between two matrices, it's much faster to compute. Okay, to code the solution, nothing. Oh, okay, so they want kind of creating one object that contains both activation and loss. Well, okay, I would do the same. To code the solution, nothing in the forward pass changes. We still need to perform it on the activation function. I think the main difference will be in the backward path. So we're not going to use the backward passes that we implemented. We're going to implement a new one, but we will use the forward pass for the previously implemented forward passes. Okay. For the backpropagation, we'll create the backward step contains the implementation of the new equation, which calculates the combined gradient of the loss and activation function. We'll code the solution as a separate class with initialize both the softmax activation and the categorical crossentropy loss object, calling their forward methods respectively during the forward path. Then the new backward pass is going to contain the new code. Okay, so I don't need this. I don't need this. I don't need and this one. Basically, this will be like in one class. Okay, we're going to, I think, still loss activation softmax classifier. Okay, let's create it as classifier. Softmax loss. We're going to have this type activation softmax loss categorical like this one. And the first thing is the activation, which is port main activation softmax activation, and the loss that will be loss category crossentropy loss. Then I will have the initialize method. Or I will call it activation for this one. Initialize. And what it does. Activation is the activation do I need to initialize something? No, it's only the forward path, and then loss, which is the loss like this, and I don't need to initialize something here. Yes, okay. So this is initialization. So the second one is forward method, and then we should have the backward method, right? We have the forward and the backward. For the forward, we're taking the inputs and the white true. So this is the similar to the activation. Where I have the activation. So I have the inputs, this one, and the Y like this. Okay, so what we're doing, we using the activation forward method with inputs, then setting the output. Why do I need to set the output? Do we use it somewhere? I don't see. Okay, it's not the first time I don't understand the code here first. And I have the output, which is dance, right? Then output equals to math dance copy of activation output. Okay. Then calculate and return the loss value. So in that case, it should return the value, right? and calculate the loss value. Loss value is the number, right? It's the number. So this plot 64, and what I need to categorical loss. Oh, this is what I have. So I have loss, calculate cross. No. It returns accuracy. Backwards. Wait. Integral loss calculate. Predictions and y. So in this case it will be output and y. Oh, because it's a loss. Okay, and the loss and the calculate function calls the forward for the loss and then uses to calculate the loss function. Okay. So okay, makes sense. So then we will be able to replace actually what we'll go. We're using the activation forward. So I think from this this one, the only thing that is kind of missing is the accuracy. We're not returning the accuracy. Okay, then let's go and implement the backward method. For the backward method, we need d values as admittance and again the ground truth labels, right? So we're taking the samples count as length of d values. So in my case, d values teams. Why I cannot do this? Why? Oh, the only thing that annoys me is this one. Okay. Okay. If labels are one-hot encoded, turn them into discrete values. Oh, okay. It's interesting how they use different approaches. So, for example, here I don't have to do anything. How I can disable it? Here I don't have to do anything because I'm already using the discrete values and not one-hot coded values, but I remember that somewhere I had to one-hot vector check. Yeah. So here I don't have to do anything. I'm not sure that I actually need the sample count, but okay. Sell the input so we can safely modify. Okay, I need the inputs. I'm not sure if I need to expose them outside. The inputs. Dense so I can safely save them. Then interesting. Okay, so what we're doing, I equal to 0, I less than samples count, then for j equals j is less than c, j. Basically what we're doing, we going through all of the inputs, right? Range of samples mean that we go over all of the... So what this line means, we going through all of the rows, then we're taking only columns that are defined here. So we're taking the column from the y actually. Oh, actually I don't need the column. So what we're doing, we taking the inputs at... Well, first we need to take the value. The value to the inputs at a, and this is interesting, like this. So that will define the continuous y variable as int value. Okay, int then we are subtracting 1 and then we're setting it back. So I int y a and value divided by what sample count. So this is how we shorten all of the... No, actually, then I need to... Okay, I will do the normalization as a second step, because I will need to go over all of them. And how I will do it, I will do the inputs apply. Func return v divided by sample count. Small element performs element wise. Okay, add again matrix. I think the only one, yeah, is the apply. We're changing a specific part of the array and then we normalizing it by the number of the samples, and that's it. And this is the combined backward method, right? I'm checking the time. Okay. To implement the solution, y hat means y. Instead of performing the subtraction of the full arrays, we're taking advantage of the fact that the y being y true is the code consists of one hot encoded vectors, which means that for each sample there is only one single value of 1 in these vectors and the remaining positions filled with zeros. So this is why we're not going through all of the columns, we're just taking the needed column from the target class, because this target thing is already kind of defines the position of the y value, of one value. This means that we can use NumPy to index the prediction array with a sample number. So this operation requires discrete true labels instead of one hot encoded labels of the additional code that performs the transformation needed. Oh, so they're describing this. I think we had something before. So basically what they're doing, they are converting so the in this case our argmax will return the index of the max value, so it will convert from the one hot encoded array of arrays into array of the indexes. But I don't need this because I'm still using only the, well, as inputs, the not the one hot encoded way, but the second one. Yeah, I don't need to do this. Let's summarize the code for each classes that we have updated. The activation softmax. This is the background. That was the hardest, I think, one that I need to implement here, and we're not using it. Okay. Crossentropy backwards. So this is the one. Yeah, so for example, here we need to expand them. That I had to implement. And this, okay. We can now test if the combined backward step return the same values compared to when we backpropagate gradient through both of functions separately. For this example, let's make up an output of the softmax function and some target values. Next, let's backpropagate them using both solutions. Okay, let's do this. To be honest, I would be surprised if they will match, but the thing is that I'm more confident in the combined version than this one, than the separate one. Okay, one test. What I'm testing? Backpropagate. So what I have? I have the soft. Okay, let's have the class target, which is the int 8 array of 1 1. Then we have the softmax outputs, which is math new dense in my case, and I have 3 by 3 load 64, and first one, second one, third one, right? And test backpropagate. They're not used. Okay. Softmax loss. Softmax loss equals to, where is it? Activation. activation. Really? No, classifier. I put it in classifier. Classifier, this one. Softmax loss initialize. Then softmax loss backwards or softmax outputs and class targets, right? And then we take in the D values. We're taking them from softmax loss D inputs and defines. Okay, so I need to make it public. I was no. No, that's the usage. Grab preview, let's be references. Okay. T print the landmark formatted D values 1. Okay, that's the first one. Okay, at least, this is what I've been telling, at least the combined version is correct, and I'm sure that we're going to use the combined version. But yeah, let's try to... Let's check the first one. Activation 1 is activation... Which one I need? The softmax activation 1. Oh no, I don't need it. Oh, output equal to softmax out, like this. Then we have loss, which is the categorical crossentropy loss. I don't need to do any initializations, right? No. Loss 1 backwards. We're taking softmax outputs and the class targets. Then we do activation. We're taking the activation when we call in the backward method again from the D inputs. And now we take in the results, and that's interesting. We have the activation 1D inputs. No, it's not exposed here too. Okay. as the inputs. And then the values too. Wow. Okay. So it turns out that I implemented the categorical cross-entropy loss backward method. Not this one, but this one. Where is it? The softmax activation backward method correctly, which is, you know, surprisingly, surprises me in a good way, because I wasn't really sure about this line, but yeah, it works. Okay, so we have the same values. Well, of course, they're a little bit different because of the floating point precision, but in general, they are the same. The results are the same. The small difference between values in both arrays results from the precision of the same here. Turns out the question of how many times faster the solution is, we can take advantage of Python's time it model, run both solution multiple times and combine the execution time. Full description of the time it model. Well, I mean, on one hand, it's interesting how fast how faster it will be in the Golang compared to the Python. On the other hand, I mean, I know it will be faster. So for example, here it's faster in 7 times. I did some optimizations with previous backward methods before, so it might be a little bit less. Although this is the good opportunity to do what? To check how I can do this in the Go. Instead of, well, let's take a code, initialize the new combine. But they don't have how they print the accuracy. Oh, okay, then they just do, but I think I put the accuracy. Where is the calculate accuracy? Where I put it? Oh, it's in the accuracy. It's just a function. Okay, you know what? I'm still curious how to do this, and then I need to replace the final code. So that will be something for me to start from next time. So where is it? I will put a to-do. To-do test how fast combined version is, and the second to-do, not here, I think. Run model. Run this one. And here I need to, yes, to do replace with the new implementation from classifier. Classifier module. I'm not sure that the classifier name is correct, but so I will start from it next time. So I will continue with this tomorrow, and then we will go for the next for the optimizers, and we'll study what is the stochastic gradient descent. And I see a lot of the code, which is good. Okay, I will put back from the place from where I want to start. Where is it? Well, this is I checked before. yeah, so this is the part I want to continue. Okay, thanks for watching, and I see you tomorrow. Bye bye.